Hello everyone, I'm Katsuhide from Group 45. This is the presentation video for comp90043 Cryptography and Security. Our research topic is ECDSA in cryptocurrency security, SecP256K1 and SecP256R1. From now on, I'll just call them K1 and R1. This is the agenda of our presentation. Firstly, I will briefly introduce the objectives of our research, followed by the meaning of cryptocurrency and types of cryptography used in it. Next, my team member Ron will explain ECDSA in detail and demonstrate how it works. And at the last, Ted will explain and illustrate the difference between K1 and R1. The objectives of our research is to compare K1 and R1 and justify why K1 was chosen as the parameters of elliptic curve in Bitcoin's public key cryptography over R1. In this presentation, we will introduce ECDSA and the difference between these two curves in terms of performance. Before we dive into the topic, some people may wonder what cryptocurrency is. Cryptocurrency is the virtual currency designed to work as a medium of exchange and use cryptography to secure and verify transactions, as well as control the creation of additional coins. There are thousands of cryptocurrency out in the market today, such as Bitcoin, Ethereum, and Litecoin. Bitcoin is considered as the first decentralized cryptocurrency since its release in 2009 and has over 50% of the share. So what is the decentralized cryptocurrency? Decentralized cryptocurrency is built from blockchain technology. A blockchain technology is essentially a database that is shared across a network of computers. Once a record has been added to the chain, it is very hard to change, because each transaction in the database is verified by checking if all the copies of the database are the same. Therefore, after a transaction is confirmed, it is unforgettable and irreversible. Cryptocurrency uses many types of cryptography. Signing algorithm is the application of public key cryptography used in cryptocurrency when signing transactions and proof ownership, which prevents double spending. As can be seen from the table, most of the major coins like Bitcoin and Ethereum use ECDSA and K1 as a signing algorithm and curve. Next, Ron will explain ECDSA in more detail.
ECDSA is an asymmetric cryptographic scheme based on DSA. The difference between ECDSA and DSA is that ECDSA uses an elliptic curve to generate keys instead of modular exponentiation and discrete logarithm. Compared with DSA, ECDSA requires much shorter key lengths to achieve the same level of security. For example, 192-bit ECDSA gives the same level of security of 1022-bit DSA. An elliptic curve is an algebraic plane curve given by a general equation: y to the power of 2 equals x to the power of 3 plus x plus b. The following 5 curves are all elliptic curves. The reason why elliptic curves can be used as an approach in the cryptography is we can make the point of an elliptic curve into a group with geometry, since it satisfies the group axiom, which is closure, associativity, identity, and invertibility. Let's define the operator dot such that P dot Q equals R, which is the third intersection point of the line joining P and Q with the curve. We define the sum of P and Q on the curve to be the reflected point R prime, or just P plus Q. We can see this operator uphold the property of closure, associativity, and invertibility. As for the identity of the group, it happens when adding P by the point at infinity O, which can be denoted by P plus O equals P. That is, O serves as the identity of this group. In the key generation of ECDSA. We add a point by itself multiple times to get the value of the public key in order to find P plus P or to be on the curve. We define P.P as the intersection point of P's tangent line and the curve. Then we can reflect the intersection point to get to P. There are some global domain parameters should be shared by the public in advance. G is the generate point. N is the order of point G. That is, N is the smallest positive integer such that M times G equals O. A and B are integers that specify the elliptic curve equation defined over Z sub Q with the equation y to the power of 2 equals x to the power of 3 plus x plus b. When generating the keys, we select a random integer d from 1 to n-1 to be the private key. Then compute q equals d times g, which means g adds itself d times. The public key is the x-coordinate of q. The reason why ECDSA is secure is given q and g. It is computationally difficult to find d. That is, point addition on elliptic curves is considered a trapdoor function. An interesting point is, ECDSA with different elliptic curves have different properties.
I'm Ted, and I'm going to show how to sign and verify with ECDSA. First of all, we hash in the transaction data into a digest Z. Then, we choose a random integer k from 1 to n-1, where n is the subgroup order, and then multiply the generated point g by integer k to get a new point p. Then, we can get the first component of signature r by using x-coordinate of point p modulo n. Finally, we can sum the digest z with r times private key and multiply this value by the inverse of k modulo n to get the second part of signature s. As for verification, we can calculate two coefficients, u1 and u2, by multiplying digest z and r with inverse of s modulo n respectively. Second, we can multiply u1 by the generated point g and u2 by the public key, then sum this point up to form a new point p. Finally, if the x-coordinate of point p equals to r, then the signature will be valid and vice versa. In the previous slide, we know that SECP256K1 is the curve used in Bitcoin. Now, let's take a look at what's the meaning of this later. First, SEC stands for the Standards for Efficient Cryptography, and P256 stands for the size of the prime number in bits, and K stands for Koplicz curve, and 1 is the version. As we can see, the coefficient A and B are defined as 0 and 7, and P is a large prime number which is close to 10 to the power of 77. And since the header is 4, the generated point G is expressed in uncompressed form, which means the first half is x-coordinate and the rest part is y-coordinate. There's another curve called SECP256R1, and the biggest difference between these two curves is the coefficient B in R1 is generated by this specific seed fitting in the equation on the slide. In the last slide, we compare these two curves in terms of security and efficiency. Usually, K1 is more efficient than R1 since it performs better on scalar multiplication. Some people believe NIS curve might have backdoor since the famous event Dual EC-DRBG, and we believe that's the main reason why the creator of Bitcoin chose a non-NIST curve in the very beginning. As for security, they are actually very close and comparable. That's all our presentation, and thanks for all your attention.